All right, number 2, we're asked to integrate some of these guys. The formulas we want to keep in mind here: the integral e to the u du is e to the u plus c, or more generally, the integral of e to the ku du is 1 over k e to the ku plus c, provided, of course, k isn't 0. So in part A, got the integral from 0 natural log of 3 of e to the 2x dx. I'm going to hit this with the fundamental theorem of calculus. E to the 2x is continuous everywhere, so all I need to do to find this integral is to get an antiderivative, plug in the top limit, plug in the bottom limit, subtract them. So using this formula, the integral e to the 2x is 1/2 e to the 2x So I plug in the top limit of integration. I get 1/2 e to the 2 times natural log of 3 minus 1/2 e to the 2 times 0. Now I want to use log properties and exponential properties to simplify this. So e and natural log are inverse functions, so they will undo each other. But before I do that, I need to bring the 2 back up as a power to make that 3 squared, or 9, minus 1/2 e to the 0. So e to the natural log of 9 is just 9. So I get 9/2 minus 1/2, which is 4. All right, in part B, we're integrating e to the negative 0.01t dt. And so I can once again directly use this formula here. It's going to be 1 over negative 0.01 times e to the negative 0.01t plus c. And then I simplify. 1 divided by negative 0.01 is negative 100. And so once again, I can check my answer by starting here, taking the derivative, and showing that it simplifies to the integrand here. That'll do it for part B. Okay, there's a lot happening in part C. So there's a couple different choices for u. I'm going to go to the old Calc 1 standby, and I'm going to let u be the thing in parentheses. So then the du is negative e to the minus x dx. So by letting u be the thing in parentheses, I'm hoping to get this to look like secant of u du. The du is this. Now the negative I can take care of by putting a negative out front. But what am I going to do about this e to the negative x? Well, I'm going to use properties of exponents to help me. This e to the x hanging out in the denominator, I can bring that up as e to the negative x. So I can rewrite my integrand as secant of e to the negative x times negative e to the negative x dx, where the negative here is because of the negative out front. And so now I can convert this to the land of u. In the land of u, this is negative secant of u du. Now we had 2 different formulas for the antiderivative secant of u du. One of them was a positive, one of them was a negative. So I'm going to choose the negative because I already have negative out front. So it's negative natural log absolute value secant of u minus tangent of u plus c. So this is going to simplify to natural log, the 2 negatives cancel, natural log absolute value secant of u, which is e to the negative x, minus tangent of u, e to the minus x, plus c. So that'll do it for part C. Alright, in part D, we're asked to integrate the quotient e to the x plus e to the negative x, all divided by e to the x minus e to the negative x dx. And once again, we're going to make a u substitution. We need to pick something good for u. So we can go back to let u be the thing in the denominator. That was one of our rules of thumb. And look what happens when we do that. The derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the negative x. So that's going to cancel that negative out. And we see that for our du, we have exactly what's in the numerator. So the denominator is u, and what's in the numerator is du. So that means in the land of u, we've got none other than the form 1 over u du. And the integral of this is the natural log of the absolute value of u plus c, which is the natural log of the absolute value of e to the x minus e to the negative x plus c. Now, of course, anytime you have an antiderivative which involves these absolute values, you have to think, do I absolutely need these absolute values? Is it possible for e to the x minus e to the negative x to be negative? And the answer is yes. It's completely possible, especially when I plug in a large negative number. If I plug in, for example, like negative 10, e to the negative 10th is a very small positive number. E to the 10th, though, is a very large positive number, so that would give us a negative inside. That'll do it for part D. All right, in part E, we've got exponential functions with bases other than e. So we're going to try to keep in mind the formula here. The integral of a to the u du is 1 over natural log of a to the u plus c. Or once again, the a's we are concerned with here are positive and not equal to 1. All right, so this is a bit frightening when we first start off. So we're going to use properties of exponents to help us out. The first thing is we can rewrite that cube root as a 1/3 power. The next thing we can do is notice that 4 is a power of 2. So we'll convert that to a power of 2. 4 is 2 squared. Next, we use property of exponent. 2 squared to the x power is the same as 2 to the 2x power. And then finally on the inside, I've got 2 to the 2x divided by 2 to the negative 3x is 2 to the 2x minus negative 3x, using properties once again of exponents. So now I've got 2 to the 5x raised to the 1/3 power, which once again I can use properties of exponents to give me 2 to the 5/3 x. So I'm finally in position to integrate this. And the integral of 2 to the 5/3 x dx is what? Well, I've got just constant multiple here. It's going to be 2 to the 5/3 x. I'm going to have to divide by the natural log of 2 because that's the base. And then to offset this 5/3, I'm going to need to multiply it by a 3/5. Okay, now, in order to avoid confusion here, one of two things I can do. I can put parentheses around the 2 to the 3/5. I can put parentheses around the 3, or I can just put a dot in the middle there to indicate that I'm multiplying. You need to somehow communicate the fact that it's just 2 to the 5/3 power, not 32 to the 5/3 power. In any case, that'll do it for part E, and that'll do it for checkpoint quiz 4.